So first thing to note is the test is not tonight. Yay, you didn't accidentally get surprised by the test, hopefully. It is moved to 1 week from today on Monday. It is going to be online, so everything that you do, you need to make sure you get it to me online. And some of the specifics aren't fully set, so I'm going to type up what is known for sure that you'll get before Wednesday, and then depending on if there's any changes from Wednesday, I'll do a finalized version of what exactly you should expect, either probably after class on Wednesday. So this is exactly the same study guide that I posted way back when, I think it was during spring break-ish. I don't remember the exact time, but it's been a while. I have not touched this document since then. This is before we went online, so there are some changes. First thing is this theory question. Normally what I do for test 1 is some nice help for you guys on the first page, and it's just fill in the blank in terms of certain things with the Hilbert axioms. Realistically, that's not going to happen now. So, in terms of theory questions, you may or may not get any theory questions, so it could be 0. They could also be incorporated into your other questions, and maybe there'll be something that's standalone as well. Now, normally I count questions based off of pages. If I'm converting this into an online Canvas quiz, that count will be slightly different. So it'll look like there's more questions than normal. There's not. It's just instead of having multiple parts under one question, they'll probably be broken up. Now, you will still need to know all of the Hilbert axioms, but you're probably not going to get something that says, hey, fill in the blank, what's the missing piece? But you might get something that says something like, okay, this is my situation. Could I use incidence axiom number, I don't know, 3. I picked on it because I could actually see it in the list. And it gives some model, some situation, and maybe it says I want to make sure that I have this second point here. Could I use this axiom? And maybe the answer would be yes, or maybe the answer would be no, and instead you should be using some different axiom. So instead of a fill in the blank, it might be some sort of interpretation question. Make sure you know the definitions of a Hilbert plane and a Euclidean plane. You might have something that simply says, hey, what is the definition of a Hilbert plane? More likely, you might have something that says, hey, what's the difference between a Hilbert plane and a Euclidean plane? And also, because I think I forgot to write it later on, one of the other things that we looked at was what a unit circle is. And I write this down because it's typically something that you will see, and people frequently, not a high percentage, but every time I've ever asked this question, it says, hey, what's the unit circle in blank model? Somebody always gives me the unit circle from trig class. In terms of definitions readily available, what I will provide you is, like normal, a list of all of the propositions. It may either be a PDF file that you can download before the start of the test, or it might be something where it's a web page that I link you to. I am in the process of testing to see which of those two I can do, and which seems like it would be easier for you guys. I probably won't include the definitions, so I would definitely recommend knowing these definitions. And I mean, the way this is going to be set up is it's online, but it's also, it's a good way to describe this. I'm drawing a blank in terms of a good way of describing it. This isn't a fully take-home test. It's like a hybrid between a take-home test and like an online fully proctored test, okay? So what that means is if you do have something in front of you, I can't police it. I'm not even going to try. So if you wanted to write out something with your own definitions, you could. However, you guys have done the homework for this class. I would not recommend trying to actually have all of your notes in front of you and look up stuff. It's just, you're not going to finish the exam in time, okay? So I would recommend studying for this the exact same way that you would for an in-class exam for our class. And then if you wanted to have a cheat sheet, again, I'm not going to even attempt to police it, but make sure if you do that, I wouldn't recommend doing it more than one page, or it's really not going to help you. Okay? But I will go ahead and provide the standard thing of all of the propositions that you'll need. It may include all of those Hilbert axioms. If I'm not going to ask you any sort of fill-in-the-blank thing, I may just put them on there, where normally I would only have one page of propositions, so it's easy for you guys to look at. I may actually put the extra page up there with the Hilbert axioms. Okay, that I haven't decided yet, but I'll get that put together for you guys, and I should have. But regardless, make sure you know how to use the Hilbert axioms. So that would be one thing that's different here with the theory questions. So just to look at the different types. Second type of question here, construction questions. For these guys, I'm still in the process of figuring out a good way of getting the information from you guys. In terms of what they are, do remember it includes both the picture and your steps have to include the citations. In other words, which axioms you use. That's the big thing about the Hilbert constructions. I am not going to claim that the Hilbert construction that you get, and it probably would be one of them, that it would be exactly from the list at the last page of this study guide, but it's probably going to either be or really, really close, something like that. This part here with the working straight edge and compass, that will be dependent on how I get this question from you. If I can actually put it into a format that's fully online, and I was looking in today to see if I can essentially enable an application in Canvas where you could actually have like a little drawing tool, which would be super cool on the question. But so far I have not been able to get that to be enabled. If I can, you could actually put the picture for your construction question into Canvas and you wouldn't have to upload anything. That would be amazing. Again, it's not working yet. So depending on how I get this question from you will be whether you actually need your compass and straight edge. If it's a file that would be uploaded, yes. If it's something that's either fill in the blank on Canvas or otherwise, then something else would be fine. Also, if you are doing this as at home and you have some computer-generated graphing program, that's totally fine for these Hilbert constructions too. All right, so that deals with construction questions. Proof questions, one or two of them. In terms of what they would look like, they would look similar to the list of sample proofs that I provided at the last page. More about that when we get there. And we mentioned this a little bit ago, but I'll go ahead and provide a list of all the propositions. And just like normal, you'll want to make sure that you cite anything you use. And then the last type of question will be our model questions. And for these guys, based on how they'll probably be broken up in Canvas, you're looking at probably 2 to 4 different questions, and that depends on whether I put them together like normal or whether I break them up as separate questions and not have a bunch of things linked together. All right, so in terms of what you'll see, the full complete model would be given to you. So, for example, in a finite geometry, you'd be given the picture. In one of our R2 models or Z2 models or Q2 models, like on your homework, in that case, you'd be told, hey, what's the description of the points? What's the description of the lines? How's betweenness working? How's line segment congruence working? How's angle congruence working? So it's got a whole little blob. If you want to see a really good example of how I would put that together, your homework set 8, as well as, oh, I forget which in-class activity it was. One of the in-class activities would have, both of them had that set up. What else? Most likely it'll be either one of the models that we covered in class. This would be specifically for the infinite models, the ones that look like XY coordinate plane, or it would be really similar to it. Like, for example, I think on the in-class activity, we had, what was it? Was it soup model on Z2? So something similar might be maybe taxi cab model on Z2. So very similar to something we've already done, but a little bit different. So those sorts of things. Okay, so that's the basics in terms of a model question. I'm not going to lie, it is pretty typical for test 2 to have probably about half of the test be dealing with these model questions, where you get like maybe one proof question, one Hilbert construction question, because let's face it, a Hilbert construction basically is a jazzed up proof. But a good majority of the test will be here grubbing around in the models. Okay, so make sure you can handle those guys. Now, in terms of some sample questions, I went ahead and listed out the stuff that we've done here. That's the Chapter 2 information. There is a little bit of a change, though. When I originally typed this up, your homework set 9 that's due today was originally 2 different homework sets, 9 and 10, and I merged them back together. So this would really just be up through homework set 9, so through the homework set that's due this Wednesday. And I don't believe there's a quiz attached to homework set 9. So the quizzes that you look at in this section are the quizzes attached to homework set 6 through 8. They should all still be viable or visible right now. And then any of the examples or activities worked in the class, and if you really have lots of time and want to look at the textbook as well, go for it. I'm not assuming you guys have that much time, though. So that would be some of the places to go look at some of the sample questions. Now, I've got some extra sample questions later on. Ooh, how to cut down on prepping time. It depends on it depends on how you studied. So you definitely want to make sure you're comfortable with all of the definitions, the axioms, the propositions, as in, what do they mean? How do you use them? But don't try to memorize them. I mean, if you want to, the more you memorize them, the easier it will be to know when to use them. But you want to be comfortable enough to get through that. Going through each question on the study guide, definitely helpful. This time, I think we have less questions on the study guide if you actually count up how many, because I know that last time I listed out all of those construction questions, and there were a lot of them. This time, there's a lot fewer of those, so that will naturally cut down on what's going on. But what I would recommend is, depending how long you spend on each question, a number of these questions are pulled from homework or in-class work, and most of those solutions are posted. So the thing would be is, I outline them and be like, hey, this is sort of the first point, second point, third point type thing, and then try to reproduce it on your own without looking at anything. And the key thing to look at there is very much, and this is most applicable to proofs, but somewhat applicable to the Hilbert constructions as well, thinking process. How did I decide what to do at which step? How did I know when to use which step? Good news, bad news. Good news is for Hilbert constructions, most people find them relatively straightforward. Why? Because we spent so much time on constructions back in classical geometry, and these guys are going to be relatively straightforward compared to the constructions we've had in the past. The big difference really with the Hilbert constructions is you want to make sure that you're not using circles, instead you're using isosceles triangles. So naturally, the workload may be cut down, but let's check that when we're back at page 3 where it lists out all those examples. In terms of content between test 2 and the final exam, that will be our third section. So our course is broken up into 3 parts. The first one, classical geometry. The second one, Hilbert geometry. And the third one is for lack of a better word, applications of Hilbert geometry. In other words, we're now going to go into essentially surveying content of a lot of different things that we could do, and we're going to go through chapters 3 through 7, but highlights only. So one of the things that I'll be doing while you guys are studying for your test 2 and after I've made your test 2 is to double check how much time we have left in the semester and how many of those content topics that we normally survey will we actually be able to do this semester. So chapter-wise out of your textbook, it looks like tons and tons more, but it's really we're going to get into survey, sort of little blurb of topic here, then jump to the next little topic. So however many weeks left, of course, is how much content we'll have left. Page 2 is all definitions here. It again talks about the Hilbert axioms, just as a warning here. Watch out for your Playfair's axiom versus the stronger version of Playfair's axiom. Stronger version of Playfair's axiom is typically only used for affine planes. Regular old version of Playfair's axiom is the one that you see the most in your various theorems of, hey, I need a geometry that Playfair's axiom holds in for this theorem to work. But for affine planes, you need a stronger version. And the difference here was parallel lines, exactly one exists, or at most one exists. Definitions, Hilbert plane versus Euclidean plane. We're going to give the definition of Euclidean plane tonight. This is for your finite geometries, incidence, projective plane, affine plane. Technically, you don't have to be a finite geometry, but that's where we talked about it. That the notion of betweenness, line segment congruence, and angle congruence, the properties attached to them can be general, but specifically how they're defined is once you get into the models. And everything down here is dealing with geometric objects, and I'm not going to lie, I literally just copied and pasted this from the definitions page on test 1. We're still looking at parallel lines, we're still looking at angles, at circles. When we had our definition of a circle before, we used the distance formula. Tonight, we're going to look at circles and the definition of a circle without a distance formula or a distance function. And it's basically the same, you just don't put in the symbols for a distance function. Pieces and parts of a circle, polygons, again, they're the same things. You just have to pay attention to what your definitions are. And the nice thing is how we've talked about the definition of these objects prior to Hilbert geometry, those definitions will still work. But here would be the distinction. Parallel lines is the really obvious one. If you're thinking about parallel lines back in classical geometry, you might think in terms of layman's terms, hey, I've got two guys that look like railroad tracks. Don't think that in Hilbert geometry. Make sure you get to the actual formal definition that's, hey, I've got two lines that do not intersect each other or have no point in common. And that would be the distinction where now you need to make sure you know the real definitions, not the layman's terms. Same notation as before. If you're comfortable with the notation before, that should be the same. The named triangle congruence properties or propositions, we still have them now. I don't normally claim to guarantee to put these on that list sheet of propositions, but if we're not going to print them out, I'll probably go ahead and make sure that they're on there even if the list of propositions surpasses 1 page. The other named things were plane separation from section 7, line separation, and crossbar theorem. So if I refer to named propositions, pretend that was an M. Those would be the named propositions. This is just making sure you're comfortable with the terminology. That way, if one of these pops up in one of your questions, you don't freak out. So here's the next actual part that you need to worry about with the study guide, and I'll do the proofs last. All right, so if we look at models, and we actually talked about most of this stuff already. So first thing is dealing with finite geometries. In a finite geometry, you're pretty much guaranteed that I will give you the picture. You need to be able to identify if that finite geometry is an incidence geometry, projective plane, or affine plane. Because I don't want to deal with getting it from you, I'm not going to worry about you guys providing an example of one of these type of guys. You might be asked to determine if two geometries are isomorphic to each other. And remember, with isomorphic, it meant you have two geometries that really, they're the same geometry, just maybe you relabeled some of the points. So here, key thing was, if they're not isomorphic, probably one of them has different number of points or lines than the other one. If they are isomorphic to each other, you're going to need to provide a map that says, hey, point A in geometry 1 really is the same as point blank in geometry 2. Yes, I'll go ahead and save this annotated version of our study guide and post that after class. So same as normal, except I don't have to scan it now because it's in electronic form. And this here, I believe these guys, I believe you had an example of these guys on the quiz that was attached to homework set 6. Okay. And then the last main thing on finite geometries is, can you tell if either version of your Playfair's axiom actually holds in a model? And this is something that's actually really, really common with models, is somebody asks, hey, does axiom fill in the appropriate blank hold in this model? So maybe you're asked something like, hey, was congruence axiom number 1 hold in this model? Like something you were asked on homework 8. Does incidence axiom number 2 hold in this model? Okay. So that sort of thing. Now that deals with finite geometries. In general geometries, specifically more of our infinite geometries, this is, does your model satisfy some property? So this would be like what we just talked about with some Hilbert axiom. Maybe you're asked to identify if your model is a Hilbert plane. Remember, that means you have all the incidence, betweenness, or congruence axioms holding. Is it a Euclidean plane? Is it neither one of them? Something else. Now, Hilbert plane requires all incidence, betweenness, and congruence axioms to be holding. So you would have to check all of them, except I'm not really going to make you do that because that would make this test like 5 hours long type thing. So instead, what would happen is, what I typically do with this type of a question to fit it in a convenient, reasonable time frame would be something like, hey, I'm going to tell you that these axioms definitely hold in the model. You check these 2 axioms and see if they hold in the model. And then if those extra 2 axioms hold in the model, then all the ones you care about work, and it's a Hilbert plane. So that sort of a thing. Or maybe, like in your homework set 8, you get to some model and side angle side doesn't hold. That would mean the last congruence axiom fails, and then automatically not a Hilbert plane. Okay? So that would be the type of thing of what you could see here. You could also be asked something about the triangle inequality. Does it work in your model? Maybe yes, maybe no. You could also be asked to, you're not going to be asked to draw because, again, I don't want to deal with getting this picture from you. So maybe it would be something like identify some triangle or circle or something else in the model. Maybe something like, hey, what does a circle look like in the model, which is something we've talked about both in homework and in class. And maybe I give you what some pictures are and you identify if any of those are circles in your model. Or maybe there's a triangle and we say something like, hey, is this triangle some question about said triangle? Okay. Also something we've done in the past. Now, I went ahead and put some extra examples of models and questions, and no lies, these exercises right here that I list in this last bullet point are totally the exercises that got pulled into in-class examples, in-class activities, and your homework questions for homework sets 6 and 8. So in terms of getting overwhelmed here, don't get overwhelmed. This is literally just looking at some of the in-class examples and work and then homework sets 6 and 8. Okay. But this here is where I actually pulled most of those examples from, just to give you some background there. So that deals with models. I don't anticipate models actually being too much of an issue, but these are ones here where I don't know the best way of studying about them. I would definitely say in terms of dealing with being able to verify these different things, you want to make sure you know what the definitions are, know what the axioms are, and how to use them are really the big thing first. Yes, for sure. So in terms of sections that are on this exam, it's sections 6 through 12. Section 10 deals with the Hilbert Constructions. Section 11 is pretty much not going to be on there because it deals with circles. We'll talk about that one tonight in like not very long. And Section 12 is the definition of a Euclidean plane. So constructions using Hilbert axioms. So this is the one that in terms of the exact way the question is going to be inputted from you guys, still up in the air because I'm checking to see what works and what doesn't. But in terms of the types of constructions to look at, these are totally just basic constructions. How to construct an isosceles triangle. We did that one in class. Remember, this is the baseline of any construction, Hilbert construction. How to bisect an angular line. We did that in class. How to draw a line perpendicular to a given line through a given point. That's going to be our first example when we get done with a study guide. And if the point is not on the line, and if the point is on the line, it's going to be one of your homework questions, or if you've already started that homework, or you've already seen it. How to draw a line parallel to a given line through a given point. I believe that's also another one of your guys' homework questions. And this last one of inscribing a square in a circle, that one is prepped up to be our last example tonight. Yes, so in terms of constructions, you're not seeing it from me just because I don't have a way to essentially videotape myself doing it. Although if it's not a live video, I might be able to get my husband to like hold the camera while I'm doing something and show you in terms of the constructions there. But yes, in terms of the Hilbert constructions, you are totally allowed to use straight edges and compasses. However, just remember, straight edges fine no matter what. Compasses, don't use the compass to draw a circle. Why? Because we have no guarantees yet in a Hilbert plane that circles and other circles or circles and straight lines intersect. We're going to get that result tonight, but it's after the constructions. In terms of the extra information, and this is the part that is totally going to change once I figure out how to actually get the information from you guys. Okay? So, if it turns out to be a file upload, please use your straight edge and compass or a computer program to do some computer generated graphics. That's okay too. Okay? Or if you actually built the specialized Hilbert tools, that's totally fine too. Okay? Now, key thing, and this is going to be true regardless of how I get this information from you, you need to write down each step that you did, and you need to reference a Hilbert axiom, okay? Or some result of a Hilbert axiom like what we did previously, plane separation. Okay? It's possible that you might be asked to show or prove that some Hilbert construction is true. Okay? You might get a non-prepped proof that says, hey, prove that this Hilbert construction actually works. If that's the case, I would most likely give you the Hilbert construction, and then the part of the question would just be the proof part. Okay? If you're asked to do a Hilbert construction, most likely you're only going to be asked to do the construction part. So picture and steps. And again, more information on this one to come once I finalize how I'll get the Hilbert construction question from you. Or if I really give up on it, not have one, but that's unlikely. All right, so last one here is, perfect question, perfect picture. Steps, yep, I'm not worried about you guys giving me the steps either, at least in terms of a technology standpoint. In terms of a perfect picture, try your best to be as accurate as possible because that normally intuitively implies to yourself that you're on the right track. But the picture is definitely secondary for the Hilbert construction. Why? Because it's specific to probably the standard model, quite honestly, as opposed to works in all situations. So it's more of an illustrative diagram instead of a full, what we would normally consider a construction, where you had to be very super precise with everything. And that's one of the reasons why, like for on your homework or whatnot, if you just wanted to use a drawing program to do it computer generated, that's totally fine too. Please don't do freehand, please, just because that gets to be a little too hard to deal with. Both, it sometimes gives you guys the wrong impression of what's really happening, and it also has a tendency to hard to read, excuse me. All right, so last thing, proof questions. So again, proof questions in terms of how I get them from you, still looking into various possibilities, but here's some of the breakdown. We have done some of these in class together. We've done some of these as in-class activities. We've done some of these as homework questions and whatnot. So first of all, there is a typo. I found this just before class. It's down here where it says 12 point something. This second to last bullet point really needs to be 12.4. That tagline really goes to the 12.4 one, and the one down here is really 12.5. I was just off by a number. All right, so proposition 6.1, we did that one in class. Exercise 7.1, I posted something about it on Canvas, and that was a homework question. 7.2, that's not a 2. 7.4 was an in-class. This is the one that had that infinitely many points were on the line. 7.6 through 7.9 was in homework set 7. And in this same section, so going along with these same type of guys, in class, for our in-class activities that we did, we actually did exercise 7.2, and related to that one, almost very, very similar, is also exercise 7.3. So those are ones that all tie in here. Okay? We talked about but didn't formally prove proposition 8.1 in class. Exercise 8.3, I believe, was in your homework set 8, and it actually was extraordinarily similar to, and this actually, if anybody noticed this, would have given you a heads up or a hint on that homework set, was very, very, very similar to proposition 8.2 in your textbook. Exercise 10.6 is something that we haven't done together. Exercise 10.9 asks you to show that right angle side side is true. We've done that in class before, but we did it back in classical geometry, so all of the reasons would need to be changed to Hilbert geometry reasons. Exercise 10.10 is in your next homework set. However, watch out. So here's a warning for the next upcoming homework set. Your book actually has a typo on this exercise, so make sure you read the directions in homework set 9, because it'll tell you how to change that exercise to actually fix the typo. It also will give you a hint on how to work that exercise, because this guy right here, this problem, is probably one of the easier proof questions on this entire list, but not the way your author gives you the hint. Exercise 1.8/12.4. 1.8 is essentially the same thing in classical geometry, and 12.4 is the guy inside of Hilbert geometry. And exercise 12.5, we're actually going to talk about tonight as long as we don't run out of time, and it's dealing with inscribing a square and a circle. Now, since our test is now online, and this guy is essentially a take-home test, and most of the solutions to these guys are posted, you need to be aware that you might get something that is not exactly this list. So when you go over these type of proof things, instead of focusing on memorizing the proof or thinking to yourself, if I write up the perfect solution and have it in front of me and I'll just be able to copy that perfect solution to the test, don't expect that will happen. Okay? Make sure you pull, when you're studying from these, the information of what's going on and why it's going on. So if you get a question that is very, very similar, but a little bit different, you can still use all of the information that you learned and apply it now to that slightly different proof. Okay? So be careful with respect to that. And that is, I believe that's everything I've got. Oh, there was one comment I wanted to write down here at the end. And the one comment at the end was specifically for models, but look at the quizzes attached to homework set 6 through 8 and the in-class activities. Just as a heads up, if you hadn't figured it out yet, the in-class activities are totally designed to help you guys with the homework, and they also sort of foreshadow test questions. They also foreshadow homework questions. Okay. So questions from you guys. That is everything I've got for you with respect to test 2. We'll have more on Wednesday, so definitely bring questions Wednesday if you have any. All right, I am seeing nothing from you guys, so I'll go ahead and post this study guide up for you guys on Canvas. The other thing that I will get up for you guys is specific details of what to expect on Wednesday. All right, so while you're typing that question, I'm going to finish my sentence. I'm going to go ahead and post what to expect for class on Wednesday, specifically for the practice test at the beginning of class, and I'll make that practice test open probably about 15 minutes or so before class. So if you want to get in there and look at it early, you totally can. I'll make sure that I have the link hopefully very prominently displayed. Right now you will not be able to find it at all because it's not visible to students yet, but I'll get all that up for you guys hopefully tonight, but realistically, because I've got tests in 2 of my classes tomorrow, it may not be till tomorrow night after those tests finish. What else? And then on Wednesday, practice test. After the practice test, we'll come back together. And if you guys find any questions that you have either on content or technology-wise, we'll talk about that after the test. And awesome! I am glad I was able to answer your question during my summary. All right, so I'm going to jump now to finishing up our content in Chapter 2. We have one last example in Section 10. We wanted to talk about circles, just a little bit on definitions in Section 11, and that's all I'm planning to do on Section 11. And then 2 things in Section 12, one the tie-in between Hilbert stuff and Euclid's element stuff, and then an example. And based on time, we should get through most of that, actually. All right, so this is the last Hilbert construction. The last time we did a bunch of different Hilbert constructions, and the main takeaway was very much, don't use circles, use isosceles triangles. When in doubt, draw an isosceles triangle. So what we want to do here is we would like to drop a line perpendicular to some given line through some given point. So let's go ahead and assume we have some line L, and we are looking at a point that's not on the line. Now, quick comment here. The homework question that you guys have for Wednesday looks identical to this. The one change is the point A is on the line, okay? And the construction, I don't want to really give it away, but it does not need to look like this at all. And in fact, it shouldn't. So in terms of this guy, what you want to do here is, well, I'm going to claim that the first thing is we want to pick some point on our line. Now, and I'm going to claim that we can totally do this by the second incidence axiom. Why? Because the second incidence axiom says every line is guaranteed to have at least 2 points. Now, I went ahead and put on a second point here, that point C. There's nothing about that point C that is required in the actual construction. I only did that for naming conventions further on down. So ignoring point C, next thing I'm going to go ahead and do is say, hey, now I have 2 points. What can I do with 2 points that I know about having in the geometry? Well, I can totally go and find the line that contains those 2 points A and B. If you want to draw in the full line, you totally can. If you want to draw in the line of B through A, you can do that too. I just did the line segment. Let me go back. So to get ourselves in terms of what we want to do, we want to find a line that is trying to be a straight line, so pretend that's sort of a straight line. So we want to find a line that is perpendicular to L through A. So we want to find that dotted line. Now, what do we know we can do? Construction techniques in Hilbert geometry are all based off of isosceles triangles. Now, there's a couple of different ways that you can do isosceles triangles. This is the stupid way. Do not draw an isosceles triangle with base A. That helps you not at all. Okay? In terms of helpful places for isosceles triangles, there's 2 places that you can do them. You can either try to make your isosceles triangle here, or so that would be ABC, not C. There's no guarantee that it actually hit point C. So what other point over there? Or you can try to do isosceles triangle A, B, and then whatever that point is. Okay? Now, I'm going to claim that one of those 2 isosceles triangles is something that we can build, and the other isosceles triangle is something that we cannot guarantee that we can get in a Hilbert geometry. Anybody have a guess on which of those 2 lines we want to try to shoot for? The one that passes through A, so this one, or the one that passes through B? Which one do you guys think that we should go for? The one through A or the one through B? I've got one guess so far. Anybody else have a guess? All right, I'm getting several more guesses in. Yes, you definitely want to do the guess of the 1 through B. Why? Because the only way to get this guy to actually work is to do some sort of circle. And we then have to have that circle center A, radius AB. It intersect here, you know for sure, because you know the point B exists. But there's no guarantee that that circle would really intersect line L in a good way or in any way. So we don't have a guarantee with this line. So what we're going to do is we're going to try to shoot for this line B right down there. So to do that, what I'm going to do is I'm going to copy the angle ABC, and that's why I went ahead and put in point C. And I'm going to copy it down here on the other side of the line L. Now, when we copy this angle, that's awesome, but we're looking for an isosceles triangle. So if we're looking for an isosceles triangle, we want those two sides to be the same or congruent. So we want to go ahead and copy AB down there to BF, specifically where those two sides are congruent to each other. Now, anybody have a guess on what the next and last step might be? Don't overthink it. We can form a crossbar. Now, crossbar theorem would be something that would go into effect here for something in the future, but just a second. Let's go ahead and, I clicked on the wrong thing. Just a second. Come back, cursor. So here we can go ahead and draw in AF, and if we go ahead and draw in AF, that line AF would totally form a crossbar on the big angle here at B, and we could apply crossbar theorem, and that would guarantee us this intersection. Now, that intersection point is what's going to allow us to prove that this construction works. I'm not going to prove that this construction works, but how you would actually do it is you would show that these two little triangles, which only exist if that point P right there exists, that those two little triangles are in fact congruent. Notice they share a side right here. They have a pair of congruent sides at A, B, and BF, and by the copying of the angle, they have both their angles at B are congruent. So you got side angle side, which is totally one of our congruence axioms. Since we're in a Hilbert plane, we know we have side angle side, or C6. So that would mean your two little triangles are congruent. Now, with your two little triangles congruent, that means these two angles are congruent, and since AF was itself a straight line, that means those two angles at P are both congruent and supplementary. Well, if you're both congruent and supplementary, that's a definition. Anybody remember what that's the definition of? Angles that are both congruent and supplementary. Yep. So if you've got a pair of angles that are both congruent and supplementary, you have right angles. And we wanted what? We wanted perpendicular lines. What's the tie-in between right angles and perpendicular lines? Just like in classical geometry, they're part of the same definition. Right angles are the angles you care about, and perpendicular lines, well, they're the lines that form those right angles. Okay? So that would be the outline of why this works. And I'm going to go ahead and I'll post the actual proof for you guys. All right, now I've got two questions that I haven't followed up on. Why were you able to have a point D? So D here, I didn't actually pull it as a point, I just did it as a label for the ray. And in terms of C4, you're right. Here, I didn't actually word it in the best way possible. So the way to reword that is you would copy the angle ABC specifically to ray BC. And then the newly formed ray would be that ray B to D. So to get angle CBD. So that would actually be the full and better way to write this out, and actually, if we did it completely, we should say that guy should be congruent to angle BAC. And I think I have one other one. So in terms of 3 points on a line, our incidence axiom I2 tells you have at least 2 points on a line. Totally fine to have 3 points on a line, 4 points on a line, etc. And in the Hilbert plane, we have all of our betweenness axioms holding. And remember, one of the consequences of our betweenness axioms is we actually get infinitely many points on a line. Not necessarily where you want them to be, but you do have infinitely many. BPC. Yeah, so to get point P right here, that point P, the existence of point P would not have come from incidence axiom number 2. This one, we would get that guy from the Crossbar theorem. And that's because we had the big angle at B. L here would be, or ray B through to C, would be your interior ray. We know it's an interior ray because of how we built the angle, part of it on either side of line L. So interior ray and crossbar theorem says you got it, yeah. So we actually walked through the outline of most of the proof anyway, so I'll write up this proof in somewhat neat handwriting, and I'll go ahead and post that for you guys. And that's it. That's the last construction I'm planning to talk to you guys about in section 10. Any last questions before we move on to definitions of circles? All right, seeing nothing from you guys, let us move to section 11, which talks about circles. We could totally spend like 2 weeks on circles. We're not going to do it. Okay? So here's the basics. We're going to talk about the definition, a couple of properties, and then the axiom that deals with circles, and that's it in this section. So first thing is we are assuming that we're in a Hilbert plane. We're not assuming that we have Playfair's axiom. So I'm not going to assume here that you have any notion of parallel lines working nicely together. We do have all of our incidence axioms, betweenness axioms, congruence axioms. So that means any of those propositions or theorems that we had from sections 6 through 9, with incidence, betweenness, or whichever type of congruence, we got them all. We also saw in section 10 that we have most of the first 28 propositions from Euclid's first book. If you want to use any of those guys, you can. A lot of this information is duplicated already, but there are a couple of new ones. Okay. So let's see what circles do. Now, we've already talked about the definition of a circle, but here it is again. So you have 2 points, O and A. O is going to be our center. OA is going to be our radius. And the circle gamma is, well, in the standard model, it's this round-looking line. Now, specifically, here's the formal definition that works in any Hilbert plane. Your circle is the set of all of the points that we'll label B in the Hilbert plane, where OB is congruent to OA. And that's also where you get your definition of all the radii are congruent to each other. Okay? So notice in this picture here, which is totally in our standard model on R2, all of these points on your circle would literally form that solid line. But as we saw when we looked at different models, the shape here can be different and still match up with our description of a circle. And this here would be what that would mean in symbols. Okay. So that's the same as what we've had before. Only difference is I didn't use the symbols for a distance function here. Now, when you talk about a circle, you also talk about parts of the circle. Inside, outside, and on the circle. Before we get there, let's look at how many points are on the circle. And I'm going to claim that we can actually get at least 2 points on the circle. And in fact, we can actually get at least 4 points on the circle. So underlying assumption, we're in a Hilbert plane. So suppose you've got some circle using the same terminology, O on the center, A, one of the points on the circle. So then what I'm going to do is I'm going to find the line in the geometry that includes both A and O. Here, I only drew out the ray A through O, but you could do the full line too. Next, I'm going to claim, hey, you could pick some point B where, and maybe you actually do put B in over here, where B is on the opposite side of the center O as A. This just ensures that you're looking at the correct side of your line. So over here, as opposed to trying to do this over there. Now, there's no guarantee that this point B is actually on the circle. It's just on the other side of O than A. So now we can go ahead and say, hey, let's copy OA here onto the ray OB, where AO and CO are congruent to each other. In other words, copy the radius over on the other side of the center. Now, at this stage, the radius and the copied version of the radius are exactly congruent to each other. So what does that tell you about point C? It must be where? And hopefully you are all thinking, yes, on the circle. And that right there tells you, hey, you are totally looking at least 2 points. Here, C and A have to be different points because they're on opposite sides of this center of the circle. So the rest of the stuff here is just going to be some properties. I didn't guess the diameter, but we did on purpose here make a diameter. So we on purpose said, hey, I want to copy this radius to somewhere else. And since we know for sure that we can grab the line that AO is on, you're automatically going to get the two endpoints of some diameter with at least that way of constructing it. So in terms of the big circle components, suppose you've got some circle. Officially speaking, all of the points inside the circle, so that includes the center as well as all other points like this point B that's not the center, those would be inside the circle. The official term is interior of the circle, and symbols, most people actually just write INT, not for integer but for interior. And notice here this just tells you that the line segment OB has to be shorter than your radius. You also can look at your points outside the circle, officially called the exterior points. So here, everybody outside the circle would be in the exterior of the circle, specifically if that line segment O to C is longer than your radius. So notice this is the official check. Two things to check, either the center or the line segment is shorter. Here, only one thing to check, if the line segment is greater. And if the line segment actually equals or is congruent to your radius, then you're actually on the circle. So that means your geometry can be divided into 3 sets. Outside the circle, inside the circle, and then actually on the circle itself. And that's it for those components. Now the next definitions we need to worry about are tangents. And there's 2 ways of dealing with tangent. One is a line tangent to a circle. So this is exactly the same definition we've had before. Your line's tangent to a circle if the line and the circle share exactly 1 point. If you have 2 circles and the 2 circles are considered tangent to each other, they share also exactly 1 point. Here's a fun fact. If 2 circles are tangent to each other, regardless of whether their radii are congruent or not, you'll actually be able to form a straight line or form a line segment that includes both the centers as well as the point of tangency. Super cool. That's actually one of the propositions in section 11, and if you've got the handout that includes all the main propositions from section 10, 11, and 12, it's totally one of them that made it on there. All right, so here's the big thing that we actually wanted to get to in section 11. So it's axiom E, which is the circle-circle intersection property. It is our, I'm probably just going to shorten it in the future and say circle axiom. But here's how it goes. You've got 2 circles. And if you look at one of the 2 circles, arbitrarily chosen circle delta here, if that circle delta has one of its points inside the other circle and one of its points outside the other circle, then that guarantees that right here, your 2 circles are going to intersect. And in fact, this guarantees that the 2 circles are not tangent, which would mean that they would actually intersect in 2 points. Okay? So that's what the circle-circle intersection property says, or the circle axiom E says. Notice it totally feels like some sort of continuity issue being forced onto circles, saying if you got something on either side, inside and outside, you're forced to go and cross that line, as several of you were mentioning a while back when we talked about circles. All right, so that's the circle-circle intersection property. Basically what it says is circles intersect nicely with each other. Now, the last thing that we've got is the line-circle intersection property, and it says if you've got some Hilbert plane and you've got that extra axiom E, automatically you're going to have this property, and it says you've got some line. If that line contains a point inside your circle, so in the interior of the circle, you are guaranteed that your line must intersect your circle. Note, this does exclude the case of the line being tangent to your circle, and specifically that's going to mean that your line intersects your circle in exactly 2 points based on previous results that we didn't actually go over all of them. Okay. So that's the crash course in circles. So let us do the definition of a Euclidean plane. So that was everything from section 11 I'm going to talk about. I posted my full notes from section 11 on Canvas. If you want to look over extra details, you totally can. So here's the big takeaway on Euclidean planes. Euclidean planes are Hilbert planes, so incidence, betweenness, and congruence axioms all hold. And you've got both that extra circle axiom, so circles play nicely, and you've got Playfair's axiom. That means parallel lines play nicely. In other words, what we actually get here is almost everything from Euclid's elements. Now, instead of doing the next couple of slides that I've actually got here prepped up with all these details, I'm just going to throw this over to a handout. So this is a handout currently posted on Canvas, and this is the conversion between Euclid stuff and Hilbert geometry and what Euclid propositions you get. And this is a chart I would recommend just keeping by you as you're doing homework for like now to the end of the semester. So if you only have a Hilbert plane, stuff we already knew, plus some stuff about circles. If you've got a Hilbert plane and Playfair's axiom also holds, well, you get everything else plus a couple of extra things. Hilbert plane with circles, previous stuff from Hilbert plane, plus some extra stuff. Euclidean plane, which is the same as a Hilbert plane, plus both parallel and circle stuff. Everything here, plus some extra stuff. And if you also have area defined, and area defined is in Theorem 12.2, you're going to get all of that previous stuff plus extras, namely all the propositions with area. And if you have a Euclidean plane plus area, well, that actually means you have everything that we played with in the past, which is all of Euclid's book 1 through 4. I'll let you guys go and check what you would need at what things. But what would happen in any situation? You'd be told, hey, you're in a Hilbert plane with Playfair's axiom. You've got this notion of area defined. Then, well, now you can use anything that we have with Hilbert geometry plus these lists of propositions back from Euclid's elements. But notice, it's not till you have both parallel lines and circles playing nicely and area defined that you have everything from Euclid's elements, or books 1 through 4 in Euclid's elements. Okay. So this is the big result of section 12. The only thing left in section 12 that I wanted to talk about was one example to see how some of this stuff is used, and we will actually be able to get through most of that example. So let me jump to it. So this example says, hey, if we're looking at both the construction and the proof of inscribing a square in a given circle, do we actually need our circle axiom or our parallel axiom? Okay, so that's the big question right here. Now, we're not going to have time to do both parts, so I'm just going to do the construction part, and I'll post the proof part for you guys. So we're going to start off being given some circle, and then we're going to try to put a square in it. So in terms of construction steps, first thing that we can do is actually mimicking what we did when we were showing that there are at least 2 points on the circle. We'll go ahead and find that line that both points A and the center are on, extend it in the appropriate direction, and then we'll copy our line segment AO to BO, where here instead of using one of the betweenness axioms, I used line separation just to make sure A and B are on opposite sides. So notice there's more than one way to do something. Now, what does this guarantee? This guarantees that AO and BO are congruent to each other. At this stage, now that we have a diameter, we'll go ahead and drop a line perpendicular to AB through that line. We'll drop a line perpendicular to AB through the point O. Now, this construction here is actually one of your homework questions, so I'm not actually going to do any of the construction steps. I just put in the line that looks perpendicular up there and labeled it L. Notice this citation is 11 from Euclid's first book, so that means it's totally something we can do in just a regular old Hilbert plane. Same deal with the 2 Hilbert axioms. They're parts of a regular Hilbert plane. Line separation, a result of your betweenness axioms, so still part of a regular Hilbert plane. We have not used either E or P yet. So next thing, we'll go ahead and copy our radius to OC and OD. So to get those 2 points, and the thing that I missed writing down here, but you should definitely include, is where C and D are on opposite sides of O. So that would be plane separation again. So mimicking step 2. Now, next stage, go ahead and form the line segments AC, CB, BD, and DA. You're just putting in line segments. This is totally cool. And at this stage, I'm going to claim that that figure ACBD is what shape? Any guesses? In other words, did we get the square? What do you guys think? All right, I got a couple of you saying yes. You guys are totally right. This guy is actually the construction of constructing a square. Now, in all the steps that we did, what do you guys think? Did we use either the circle axiom or the parallel line axiom? We did not at all. And one of the ways to check that is on that sheet, that chart right here. If we'd use something like, oh, I don't know, 320, so book 3, proposition 20 right here, this would tell us that we would need to be in a Hilbert plane with both P and E holding. So in that particular, that's one of the ways that you can tell, hey, how do I know if I'm going to need one of these extra axioms or not? That's why I say chart here is nice. But in this particular case, nope, we used all things that were just in a normal old Hilbert plane. So simply for the construction part, we can get that figure straight up, no extra axioms. Now for the proof of this, to make sure it really is a square and it really is inscribed in the circle, you do the same thing. You'd walk through your proof, and then at the end you'd check, hey, did I use anything that requires either the parallel axiom or that extra circle axiom? But I'll go ahead and post the proof part, and it turns out you can actually get away with not using either the circle axiom or the parallel axiom. You just might have to do things a little bit different. For example, here on this line L, we didn't say find point C and D where the line intersected the circle. We copied the radius onto the line L. We copied the radius onto the line L, then both top and bottom, and that's where we got our points. Not from intersections, but from actually our definition of how a circle is supposed to behave. But that's some of the ways of getting around using some of those extra axioms and converting something from a classical straight edge and compass situation to the Hilbert situation that works in any model. But that's literally all I got for you guys for tonight. Sorry we ran over just a little bit. If you guys have any extra questions, I'll hang out for a little bit tonight. Feel free to shoot them my way, but that is everything I've got planned for us for tonight.